Have you ever wondered how engineers can predict if a complex system, like an airplane's autopilot or a power grid, will remain stable under various conditions? It is a critical question for safety and performance, especially when dealing with feedback loops. Interpreting a Nyquist plot for stability fundamentally involves counting the encirclements of a specific point on the complex plane, often referred to as the -1 + 0 j point. The number and direction of these encirclements tell us directly about a system's stability. The core mechanism behind this interpretation is the Nyquist stability criterion, a powerful tool derived from complex analysis. It relates the number of unstable poles in the open-loop transfer function to the encirclements of the -1 + 0 j point by the Nyquist contour. Essentially, it helps us determine if closing the feedback loop will result in an unstable system, without needing to calculate the closed-loop poles directly. This works because the plot essentially maps the system's frequency response onto a complex plane, allowing us to visualize potential instability. To apply this criterion, first, draw the Nyquist plot for your system's open-loop transfer function. This plot traces the response of the system as frequency varies from 0 to infinity and then reflects it symmetrically for negative frequencies. Next, count the number of unstable poles the open-loop system has, which are poles in the right half of the S-plane. Then, carefully count the encirclements of the -1 + 0 j point by your Nyquist contour in the clockwise direction. The system is stable if the number of clockwise encirclements plus the number of open-loop unstable poles equals 0. If this sum is anything other than 0, your closed-loop system will be unstable. A key concept here is the gain margin and phase margin, which are often read directly from the Nyquist plot. These margins provide quantitative measures of how much the gain or phase of a system can change before instability occurs, acting as crucial indicators for robust control system design. A large gain margin, for instance, implies that the system can tolerate significant increases in gain without becoming unstable, offering a useful safety buffer. Understanding Nyquist plots allows you to proactively identify and mitigate potential instability issues in feedback systems. By visualizing the frequency response and assessing encirclements, you gain a deep insight into how robust your system will be, enabling you to design control loops that perform reliably and safely across their intended operational range.